next unit means the fourth unit. Now, fourth unit has 2 chapters. Okay, chapter wise they are different, but unit wise their values will be different. Okay, so see, when I'm talking about the unit, this is unit 4, which has 2 chapters, EMI and AC. Okay, EMI and AC, these are two. Now, look here, chapter 6 is your electromagnetic induction. Electromagnetic induction. This is the formula. This is the full form of EMI, electromagnetic induction. And then you have the 7th chapter. AC means alternating current. This means alternating current. Okay. This is the 4th unit, EMI and AC. Chapter 6 is electromagnetic induction. Chapter 7 is alternating current. And both are from your NCERT. Okay. In this same manner, they are given in your NCERT. Fine. Now, see, when we start with the chapter, I'll start with chapter EMI first as given in the sequence. Okay. So this will be electromagnetic induction. Now, look, Basmi, the question that we had earlier, the question was that if there is a current carrying wire, will it produce the magnetic field? Or that the initial question was there. Current is there, current carrying wire. If it is existing, current is there, current carrying wire. Current carrying wire, will it produce magnetic field or not? The earlier question was this. But we saw the whole Biot-Savart law and the whole chapter, everything we saw. This wasn't the case, right? Magnetic field was there, magnetic field was existing. The complete Biot-Savart law gives us the magnitude also, right? Yes, this exists, we know. But now the question came, what if magnetic field is existing? Okay, magnetic field in a wire or a coil anywhere, will it give rise to current on? Now the question was that magnetic field is there. Now, if the magnetic field is there in a wire or a coil, will it produce any current on? Okay, so from this chapter, we'll realize that yes, this is also existing. It's not just what we've studied, that magnetic field current will only give rise to magnetic field, and magnetic field can only be created independently. That was right. We saw various sources of magnetic field, solenoid, toroid, they were producing magnetic field. Lots of things were there, right? So yes, magnetic field in a wire or a coil will produce. So we did a topic, electric flux. What was the meaning of electric flux in the first chapter we've done?
The total electric field in a surface.
Total?
Into a surface. Number of electric field lines.
Electric field lines entering a surface, but one condition, they have to be perpendicular. We only take the normal ones, right? So here also look. Let's say this is a surface. So see, very easy. As I told you, first 4 chapters have completely different topics. From 5th onwards, you have the topics mixed and matched. Now see here also, if I have various magnetic field lines. Okay, various magnetic field lines are present. And these various magnetic field lines, they are making an angle of 90 degrees here. Means all of these are perpendicular. Okay, this is also 90 degree, this is also 90 degree, this is also 90 degree. So we can say the flux is magnetic flux, you just put B here. Now, whenever you have any exam or anything, because after magnetic flux is done in your school, you write this as E, this symbol as E for electric flux, and this symbol as V for magnetic flux, so that it becomes clear, because flux has the symbol phi. Okay, magnetic flux is now, see, you count the number of magnetic field lines that are crossing the area perpendicularly. Let's say this is 4, so I'll say the magnetic flux is 4. So it's very easy to answer. These kinds of questions we have already done, right? So number of magnetic field lines crossing
Yes,
area normally. When we say normally, that means perpendicularly. So normally word has to be there, okay? And if you're not writing that in your statement, then your answer will be wrong because the concept is completely wrong. Number of many magnetic field can enter. Now, problem here is that every time counting the magnetic field lines are also not possible. We need a particular formula that even if we have a variable surface, we are able to calculate its value. So that we'll be able to do here.
ma'am.
See, number of magnetic field lines crossing, let's say there's a surface. Exactly same thing, you have done this in the electric flux. This is a surface. Now, what do we do here? The surface area is the S. Here we take a perpendicular to the surface, and this perpendicular will always be taken, that is our area vector. Here also we'll have the area vector again. Okay, so this is the area vector, that is n cap. Remember, this has to be taken. If you forget this, then your answer will be exactly opposite to what you will get. And you've done the questions in electric flux also, so I hope you'll be able to recall that. Let's say magnetic field lines are anywhere at any angle to this surface, but you are not concerned with that surface, you are concerned with this angle. So you'll always take the angle between the perpendicular to the plane and the magnetic. Okay? Just a minute.
Ma'am.
Yes. So see, you take the angle between the area vector. Area vector means perpendicular to the plane and the magnetic field. This is the angle that you will be taking. Okay. Now see here, you have the surface area as S. So electric field is taken as, sorry, not electric field, magnetic flux. Magnetic flux. Here, magnetic flux formula is exactly the same. That time it was E dot A. Here it will
Yes,
be
ma'am.
B dot A. But again, I'm saying just mark B here because right now we are just doing magnetic. So, you know, nobody is going to ask you electric flux in this chapter. But when it comes in your finals, that time nobody will segregate the chapters for you. So you'll have to write the variables wisely. So yes, this is equal to B dot A, which can be written as integral of B dot dA. Also, see, this is B. B is the magnetic field. A is the area, right? This
Yes,
can be
ma'am.
expanded as B A cos theta. So which formula do you have? One formula is this. Second formula is this. Okay?
Okay, ma'am.
All right. Write down, note down these things properly.
Can you scroll down? Can you scroll down? Ma'am, can you scroll down? Done, ma'am.
Okay, look here. For this magnetic flux, the unit is different here. Okay, SI unit is Weber. This is written as WB. Again, it's a scalar quantity, so you can use the scalar addition of it. Scalar addition means where you have to subtract, you will subtract. That doesn't mean you just have to add. Scalar addition means no vector quantity. Okay, so let's see some questions. It says magnetic field of 2 Tesla exists in space. It is inclined at an angle of 30 degree with the plane. Calculate the magnetic flux through it if the area is 10 meter square. Look, here you tell me the values that are given. What is the magnetic field given?
2 Tesla.
2 Tesla. Yes. And area is
Area is 10
10.
meter square.
10 meters. Yes. Angle
Theta is 30 degrees.
given with
Okay.
respect to the plane. See, this is the plane surface. This is the magnetic field. This is 30 degree. We don't choose this. We choose this angle. And this will be 60 degree. You have to take the area vector. Okay, so this won't be 30. This will be 60 degree. So now when you use magnetic flux is equal to B dot A, which is equal to B A cos 60 degree. So look, it becomes 2 into area is 10 into half. So this becomes magnetic flux becomes 10 Weber. Okay. Write this from here. Write down these 2 points as well.
Ma'am, can you scroll down? Done.
Done?
Yes, ma'am.
Okay. Let's see one more question. See, this gives us the magnetic field as 10 I cap plus 3 J cap plus K cap. Okay. And it says there's a space that is existing in the YZ plane. Let's see, this is Y. This is coming out Z in this plane. Okay. The area is 2 meters square. So see, for the surface area, this is 2. But which unit vector should I put, Basmi?
Why is that plane so K cap? I
K
guess.
cap.
Yeah.
Why?
Ma'am,
What's the first step that we talked in the magnetic flux?
it should be perpendicular to the plane.
Yes.
Not that. Yeah.
Area vector will be perpendicular. Where is the area vector going?
Oh, yeah. I cap.
I cap. Okay. Now, this is P dot S. Now tell me, 10 is there? This is 2. So 10 into 2,
I cap.
10 into 2 minus. Now 3, here nothing is there, so 0. Sorry, the plus. Here it is 1 into, here it is. So we will straight away have our answer. Magnetic flux will be 20. And yes, what?
Ma'am, won't I cap come? I cap, J cap.
I cap dot I cap J cap
Oh,
dot
yeah.
J cap K cap dot K cap is equal to 1. Okay, so this will be simply Weber. If this was a cross product, then something would have come, but not in this. Okay, write down this question and then we'll do some other topic. Faraday's experiments we'll see.
Can you scroll down? Done, ma'am.
Okay, there were certain experiments conducted by Faraday. Okay, so these experiments are known as Faraday's experiments. So basically, what did he do? He observed that yes, whether if you have a magnetic field, does it produce a current or not? Okay, will there be a production in the current or not? So that was the main aim of Faraday to find out. Okay, because see, according to Biot, this was very clear that magnetic field is there, current carrying wire is there, it will definitely produce a magnetic field. But the problem came with the current reverse. Current will produce magnetic field, that was fine, but magnetic field producing current, that was a tough thing. So what did he do? He had a coil. He took a coil. Okay, and with the coil, what did he do? He had this, let's say this is a coil. He took a wire and turned it in this form. Okay, this is how he turned it. This shape and this way. And he connected a galvanometer. Now, what is a galvanometer? You've given the homework also. By now, you should know.
What do you mean the what is the galvanometer? It's something
What?
that has
Something that has
electric current to measure electric current.
stores electric current.
No, ma'am, measures. I think it measures electric current. Yeah.
That is an ammeter.
Oh,
Ammeter measures current. Galvanometer can never measure current. We did it in so detail. I showed you figures also. We saw the inner structure of it also. It detects current, whether current is existing or not. It cannot measure current. For measuring, you have ammeter. Okay, measurement, ammeter, voltage measurement, voltmeter. But just an answer that will give you whether a current is existing or not will be done by galvanometer. Now remember that. Okay,
okay, ma'am.
go through again. So let's say this is a galvanometer present. So this is just copper wire turning in this in the form of a coil. Now what was done by him? He took a bar magnet, north polarity, and he moved the magnet closer to this coil. It was observed that yes, this galvanometer showed a deflection here. The galvanometer showed a deflection. Means see, because of this, there must be magnetic field lines coming. Magnetic flux would be there because of the magnet. But galvanometer is showing deflection. When a galvanometer shows deflection, that means current is existing in the circuit. So here what happened? The galvanometer showed a deflection in the circuit. This concluded the fact that if galvanometer is showing deflection, so this shows that current is existing. means there was a current in your circuit that is determined, which was the question earlier. Okay, that was one experiment. Second experiment that was done, again the coil was taken. A galvanometer was put. I just mark the arrow because G is used for the resistance of the galvanometer. No? Mostly. In the last version you have used RG also. That is also fine. It should but just mention that what is the resistance of the galvanometer. Okay, so this is it. Now see, it was observed that here instead the coil was moved. Here at least this was there that the coil was at rest. Coil was at rest. But here the coil is moving. When we talk about here, the coil is moving. When the coil was moving, the magnet was put as it is, but the coil moved. It was noted that due to the movement of the coil also, the current was produced. A current was induced in your circuit. In your system, a current was induced. So a current was induced in your system, and so because of this current, an EMF was induced in your system. This is the voltage. Now, what is this induced current, inducing EMF and all that we have to do in this chapter in detail. Experiment done by Faraday. What did he do? He took an iron rod and he wrapped wire on, and then he connected one end of the wire to a battery, which was connected to a key and which was connected to a rheostat. What's a rheostat?
Wow.
Device that changes the resistance. Device that changes the value of resistance. I have told you this. You will see this in your lab also. There is a slider over it through which the resistance can be changed. And the other end was tied to a galvanometer. So it was observed that yes, the current was produced and galvanometer was there. But this we'll be doing in alternating current because the kind of current that is obtained is alternating current. But yes, so all these experiments gave one conclusion that magnetic field is existing. When magnetic field is existing, current is also existing, the vice versa of the Biot Savart. Okay.
Yes,
So
ma'am.
write a little about these experiments in words I have not written so that you're able to understand when you need to figure this.
Yes, ma'am.
Okay, please write.
Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, can you scroll down? I'm done, ma'am.
There are certain conclusions from this. First is that it is observed that whenever you have the magnetic flux, okay, this will give a magnetic flux. Basically means the magnetic field. Okay, so when we're talking about the magnetic field is giving you the current. That is one conclusion. The conclusions come in the board exams to write. Okay, second conclusion is that when the value of this magnetic field is more, the more is the amount of current produced. Okay, and if the current is produced in your circuit according to Ohm's law, you will have the voltage as well, right?
Yes, ma'am.
So the current, see, there wasn't an actual current in your circuit flowing through a battery or a cell producing it. There wasn't any current, but because of the change in the flux, when the magnetic field changed, it led to change in the flux.
Yes, ma'am.
So because of that, the current is coming in your circuit. So these type of currents that are produced, they are called as the induced current. Okay. And the EMF is also known as induced EMF. So see what is the conclusion. Whenever the magnetic flux linked with the closed circuit changes, an induced EMF and hence an induced current is set up in it. Means magnetic flux changes, current and EMF will come. And higher the rate of the magnetic flux with closed circuit, the greater is the induced EMF or the current. Means this gives us a hint that yes, magnetic flux is depending on how this EMF is changing. Yes, so these are two conclusions based on which Faraday gave his law. Experiments he did, these were the conclusions. Now write down these statements. Then let's see what is the Faraday's law actually. Okay, write it.
None, ma'am.
See, coming to the Faraday's laws of EMI. So first point of Faraday's law is that whenever you have the flux getting changed, there will be an EMF produced. That is what we have seen. So we can say here the EMF produced is directly proportional to the rate of change of the magnetic flux. Okay, this when I say flux here, I'm referring to the magnetic flux. E is directly proportional to what this is? This is the rate of change of flux. See, if the flux changes at a very high rate, the flux is changing, lots of values are changing with respect to time. So we get EMF is directly proportional to d phi over dt, right? Now change in the flux, we can also say that this can be written as equal to with a minus sign. Now why a minus sign, that we'll talk later. Okay, I'll tell you this. Phi 2 minus d phi 1 over dt. So the final formula of EMF becomes E is equal to minus d phi over dt. This is the formula of the EMF. What is E? E is the EMF of the circuit. And this is not the original EMF that is present. This is the induced EMF. Okay. Minus sign we'll talk in the Lenz law. This minus sign is given by Lenz law that we'll talk later. And this whole term is the rate of change of flux. Okay. Now see if R is the resistance. So we know E is equal to IR.
Yes, ma'am.
E is what? D phi over dt. It is equal to IR. So from here, the value of induced current will be minus 1 by R d phi over dt, where R is the resistance. Now let's say Q is the charge. We know I is equal to dq over dt. So look, can I say dq over dt is equal to minus 1 by R d phi over dt?
Yes, ma'am.
Dt will be cancelled. So from here we can say dq is equal to minus d phi divided by R. This is the charge. This is the change in flux. Change in flux. And while this R is the resistance. Okay.
Ma'am.
All right. Write down all these points. This is these are the Faraday's laws of EMF. So first point is that there will be an induced EMF. Second point is that it will be directly proportional to the magnetic flux. Okay, so this is what it is written here. Whenever magnetic flux linked with the coil changes, an EMF is induced, which is directly proportional to the rate of change of magnetic flux. So these are the two conclusions. First point is that magnetic flux will be induced. Second is that it will be directly proportional to the rate of change of magnetic flux. This has to be remembered, okay?
Ma'am.
All right, write it. Write this. Faraday's laws of EMI.
Ma'am, can you scroll down? 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 Yeah, ma'am, done.
Okay, see, this question says 10 ohm resistance coil has 1,000 turns, and at a time 5.5 into 10 to the power minus 4 Weber of flux pass through it. Okay, so this is the initial flux. Then it says it falls to 0.5 into 10 to the power minus 4 Weber. So this is the final flux. Okay, initial flux is 5.5 into 10 to the power minus 4. The final flux is 0.5 into 10 to the power minus 4. Now, this says number of turns are also given. N is given as 1,000. And the resistance is given as 10 ohm. It says you have to find the EMF. Time is also given. You have to find out the EMF generated in volt and the charge flow through the coil in coulombs. See, EMF, we know EMF will be minus d phi over dt. Minus this d phi means when you have such finite values, you can use this formula also. E is equal to minus delta phi by delta t. Same thing. For finite values, you use the bigger one. So phi 2 minus phi 1 by T2 minus T1. Now, second flux is given as, this is minus, this is given as 0.5 into 10 to the power minus 4 minus, this is 5.5. 5.5 into 10 to the power minus 4. This is the flux divided by time is 0.1 seconds. So this is equal to minus 0.5 minus 5.5 minus 0.5 is 5. So this becomes minus 5. into 10 to the power minus 4 divided by 10 to the power minus 1. So this makes it 5 into 10 to the power minus 3
Minus.
volt. Okay, this is the EMF. Now see, for the charge, we have studied it is flux divided by the resistance. Right? Here, so when we are talking about the charge, dq is equal to whatever is the change in the flux minus delta phi divided by the resistance. So this is coming minus 5 into 10 to the power minus 3 divided by resistance is 10. So this becomes minus 5 into, this goes up 10 to the power minus 4 coulomb. Okay?
Okay, ma'am.
All right. Is that clear, Basmi?
Yes, ma'am.
Please write one more question, we'll see.
Ma'am, can you scroll down? No, I'm done.
Look at this question. See, it says a coil is there of cross-sectional area A, and this lies in a uniform magnetic field. Lies in a uniform magnetic field perpendicular to the field. Okay. So in this position, normal to the coil makes an angle 0 degree with the field. It says then the coil rotates at a uniform rate, okay, to complete one rotation in time t. Now, what do we have to calculate? Average induced EMF in the coil during the interval when the coil rotates between 0 to 90 degree. See, this rotation of the coil and all, you will be able to understand better in the chapter alternating current. There we have this. What is the equation for it? How does the coil rotate with different angles and all that is there in case. Right now, why is it a part of this? Is because here you don't have to do anything with respect to the yes, I was saying you don't have to do anything with respect to the coil. Okay, the rotation of the coil, you don't have to do. See, imagine this is 0 degree, 0 degree or 360 degree, 0 degree, here 90 degree, 92, 180 degree. This is 270 degree. This is 360 degree. This is how the coil is rotating. Now, it's like from the top view, if you look, coil is like this. Then coil is like this. Then coil is like this. Then coil is like this. This whole pattern we'll see in alternating current. There we'll calculate the induced EMF using different methods. Right now, you know, the area is given as A. Magnetic field is B. Okay. You just need to find out the time. For EMF is phi by t. You just need to get the time. So look, in the first part, it says it is going from 0 degree to 90 degree. And it also says the total time covered is t, means in one rotation. One rotation means to start from 0 and to come back to 0, the time taken is t. Total time for one complete rotation is capital T. Okay. Now, if in the first part it is going from 0 to 90 degree, can you tell me how much portion from the time has covered in this? What will be the time here?
1/4.
1/4. So total is T, so this becomes T by 4. Now, look here. If this is T by 4, that's the time. Coming to the flux. You have first, let's say, initial flux. This is B dot A. That is BA cos. Now see, initial angle is 0 degree. Right, initial angle is 0 degree between magnetic field and area. This is the area of the coil, magnetic field is there. So this becomes BA. Final flux will be B dot A again, but BA cos
90.
90. So this becomes 0. Now let's EMF. What is EMF? It is minus D final minus D, or I'll use delta because this is also not changing with respect to anything. This will be minus final flux minus initial flux divided by the time. Minus of final flux is 0, minus initial flux is BA divided by T by 4. Minus becomes plus BA by T by 4. 4 goes up. Finally, we can say 4BA divided by T. Got it?
Yes, ma'am.
Second part, tell me how much time will be taken?
It will be T by 2.
Why T by 2?
No, it's from 90 to 180. It's T by 4 itself.
It's T by 4 only. In the second part, see, in the second is the Okay, so this is a question from your NCRT, and there are various angles given from 0 to 180 degree, 90 to 270 degree, 270 to 360 degree, 0 to 180 degree, like this. So same method. Rest of it you will find it in the textbook. So see, time here will be T by 4 only. Now initial flux will be B A cos 90 degree. It will
Yes,
be 0.
ma'am.
Final flux will be B A cos 180 degree.
180
Yes. What is cos 180?
-1.
Yes, minus 1. So this becomes minus BA. Yes. Now see, coming to the EMF. EMF is minus final flux minus initial flux by the time minus, this is minus VA minus 0. It's coming the same. Look, minus will again become BA divided by T by 4. 4 goes up, that is 4BA by T. But this is not fixed, that you will always get 4BA by T. In these two parts it was coming because time was also not changing. You change it from 0 to 270 or anything. That's how you got it.
Yes, ma'am.
So that completes with the topic. Now the next topic that I'll start is Lenz's law. Why that negative sign is coming. We didn't talk about it, no? Why sign is there.
Mm.
Okay, write it.
Mm.
Your next class will be on Friday. Okay, not tomorrow. Okay.
Ma'am, can you scroll down? Can you scroll down?